Yeah, thanks for the invitation to speak. Am I audible? Can people hear me? Yes?
Yeah.
Okay, awesome. Yeah, so thanks for the invitation to speak again. And I'm going to talk today about the Motivic Cohomology of schemes, and all of the things here are joint work with Tom Bachmann and Matthew and various incarnations. And yeah, I'm really sad I cannot be in France. Mostly I'm sad because I cannot see some of my friends there, but also because I cannot enjoy this fantastic Indian restaurant in Gaduno called Sundarban, which I highly recommend everyone go. Okay, yeah, so all of this work is to appear, and so this is kind of the plan of the whole series of lectures. So I'm going to talk today about classical motivic cohomology, maybe from a quite quirky point of view. And then I'll talk about some CDH methods, which will have heavy overlap with what Georg is going to talk about. And then I'll talk about this new motivic cohomology, which is produced in joint work with Matthew. And the notes are on my website, by the way. I hope it's obvious. It's like in the very first page. It just says lecture notes in IGS. All right, so this is a picture of motivic cohomology that I ripped off from Dan Grayson's paper with filtrations on Algebraic K-theory, where he surveyed the development of motivic cohomology. And I hope that this picture will be kind of more friendly to everyone in the audience at the end of this talk. All right, so I want to start by motivating what motivic cohomology is. So to X, I can assign this abelian group, in fact, a ring called K0 of X, which is the Grothendieck group of vector bundles on X. So this is a very easy to define invariant, but it's actually very subtle, and it contains a lot of rich and deep information about algebraic cycles on X. So for example, as an example, we can look at the simplest kind of algebraic cycles, which are line bundles or codimension one cycles. We are in some smooth situations, so all of those agree. So there is an inclusion of the Picard group into K of X, and this map is split by the determinants. So I of X is a particular injective, although I should warn that, of course, this is not, determinants is not a homomorphism of abelian groups, since it's going to convert addition to multiplication. So you cannot really say that K0 of X is in general splits off the Picard group as a group, but yet we know that it at least contains as much information as the Picard group on X.
Excuse me.
Yeah.
What you said, I think it's the other way. That is the determinant of a direct sum of vector bundles is the tensor product, which is the addition of the Picard group, but the map IX.
That's right.
It's not clear how to define it because you want it to be of rank 0, so you have to subtract O, but then it's not a homomorphism. In general, it's not. The first one is not. You cannot make the first one into.
That's right. Yeah. Thank you. It's not. Yeah, it's not group map exactly. Thank you. Yeah. Of course, determinant sense direct sum to product, tensor product. All right. So, if it's a smooth scheme, then I can also I can peel off various parts of the child groups of X in the following manner. So we know that K0 of X, when you're smooth, is isomorphic to G0 of X, which is the Grothendieck group of coherent sheaths on X. And so I can look at the following subgroup in G0. So this is called FJG0, which is a subgroup generated by the classes F, such that this F is a coherent sheaf whose codimension of X, of the support of F, rather, of F, is greater than or equals to J. Okay. So from this point of view, I get a decreasing filtration where I have G0 of X, and then which is F0, which is the biggest piece of the filtration, and it goes down. Okay. All right. So there is a canonical map from the child groups of X into this graded piece of the filtration that just assigns a cycle into OZ, the class of OZ, which is now a legit coherent sheaf whose support is like the codimension of Z. And part of Riemann-Roch says that this map is in fact surjective, and the kernel is killed by this J-1 factorial. So in particular, we learned that after rationalizing So if I take Child groups of X and I just rationalize, that's isomorphic to this K0 rationalize. So you see, once I rationalize K0, you see that this K0, which is kind of easy to define, contains all information about algebraic cycles within X itself. Yeah. So this the higher K groups is kind of the main topic of the summer school, of course. And one reason why you might want to care about the higher K groups is that it kind of measures the failure of this K0 to have some kind of descent in some sense. So let me explain that. So if you have two open subschemes of X, U and V, such that X is covered by U and V, then we have this exact sequence at the bottom where you have K0 of X restricting into these two opens and then restricting to the intersection. And this map to the right is surjective in general as long as X is smooth. But this map on the left is not in general injective. So this is what K1 does. K1 is the thing that sticks in here. So you have K1 of U intersect V, and then you go down and it wraps around via connecting homomorphism. And this kind of pattern extends. And this is how the higher K groups sort of accounts for descent phenomenon in algebraic K-theory. Okay, that's like kind of a standard motivation as to why you want the higher K groups. And so it's kind of reasonable to ask the following analog for child groups, since we see that both child groups and K-theory are very much have an intimate relationship. So if you fix a J, then we also have this exact sequence at the bottom where you have child J of X mapping into these two opens into child J of the intersection. And one question that we can ask, which has a more modern solution than higher K-theory, so to speak, is that you can ask if there are these groups that sort of rectifies the failure of this map to be injective in general. Any questions so far? Feel free to, I guess, scream questions if you like. Okay. So I claim that when J equals to 1, this is kind of quite familiar. So you have the Picard group below. This is just the case when we have child 1. And what you can stick in here is nothing but the units. So you have O cross of U intersect V. And you can put here O cross of U direct sum O cross of V, and you have O cross of X mapping to. So indeed, the kernel of the map from Picard group of X into these two intersection is basically just the gluing data at the intersection, which defines for you units in U intersect V. So Motivic Cohomology is in some sense just a very fancy or very enhanced version of this particular picture. There's some kind of cycles thing here and there's some kind of units thing at the back, if you like. I mean, there's a very an extremely naive kind of point of view, but it turns out to be, I think, kind of powerful to gain some intuition about what Motivic Cohomology is all about. Okay. So since we are kind of adults, the correct formulation for descent is not really just the long exact sequence. So long exact sequences comes from certain homotopy Cartesian squares on the level of spectral chain complexes. So indeed, the correct formulation is if X is covered by these two opens, then we have a homotopy Cartesian square like this, where K of X is covered by this K of U and K of V, with this vertex being KU intersect V. So the correct question that we want to answer is that if J is greater than or equal to 0, are there these complexes ZJ modes such that it converts the square? So you have U intersect V, mapping to V, mapping to U, mapping to X, which is Cartesian, and some degree, and this degree will be clear in a moment, some degree of it is exactly the child groups. Right. So you want to produce these complexes, which converts the Zariski square of X, the Zariski cover of X, into a homotopy Cartesian square in order to get these long exact sequences that I mentioned at the beginning. Okay, so here's the theorem. I mean, this is like just looking ahead. So I put it in quotes because I kind of want to be a bit vague here. So what we want at the end of the day is to enhance this relationship between child groups and K0 to the level of higher K groups. And the correct theorem that one wants to prove is that for any X, which is a smooth scheme over a field, there exists a filtration. So this is a filtered spectrum. So it's just a sequence of spectra, field 0, field 1, field 2, and so on, such that it has good properties. So for example, you can ask that this filtration be compatible with the multiplication in K, but I'm not going to make that precise for the moment. Because you can ask compatibilities like that. And out of this filtration, I can extract its graded pieces, which is just the cone of the different layers of this filtration. And you want these graded pieces to produce this Motivic cohomology complex. You want it to produce these complexes up to some shift. Yeah, so this GER star is just the co-fiber or the cone of the map between field star plus 1 to field star. And you want something like the 2J, J power to be the higher Chow groups. And since we see that there's nothing to the right, or rather the map from Chow groups U direct sum Chow groups V to Chow groups U intersect V is surjective, since there's nothing on the right, this cohomology vanishes above degree 2J. It's at least some requirement that we might ask. So this open mirror Viatoris is exactly this homotopic Cartesian square that I talked about in the previous slide. And you want to recover this rational decomposition of K0, and in particular, you also want to enhance it. So you ask that the spectral sequence you obtain from this filtration degenerates after you tensor with Q. So if you can even ask for a stronger statement, namely that the filtration actually splits. Okay, so this is kind of the theorem that we want, and we'll revisit the status of this theorem later on, maybe at the beginning of talk 3, at least when X is smooth. But for now, this is the picture that I want you to have in mind. That what you want to do is to extract some kind of higher algebraic cycles, which kind of refine higher algebraic K-theory. All right. So today I want to give a rather maybe weird viewpoints, which kind of aligns with how Motivic cohomology is enhanced to the case of singular schemes. And it's this handcrafted viewpoint. Okay. And in some sense, this is kind of illegal. You're not really allowed to define objects via some pullback squares, via some one of these fracture squares, but I'm going to push it on anyway. It is, I think it's kind of enlightening. There's a lot of different, textbooks and references on Motivic cohomology, and this one I think is like less talked about. So I think it'll be kind of interesting. So the handcrafted viewpoint is the following. So I want to produce Motivic cohomology by declaring what the rational parts are, what the P-complete parts are, and what the rationalization of the P-complete parts are, okay, as P varies across all primes. So what we will do is we'll define all these objects, Qj, Zpj, and so on, and we'll take the homotopy pullback, Zpj, not P, of course. I'm going to take Zj modes as this pullback. Okay. And in fact, all of this Zpj is going to be defined as the homotype limit, as this Z mod P to the nu J varies, as nu varies across all numbers, going to infinity. So I'm going to declare this like mod P parts for all P, and then I'm going to glue it together with the Q part. So most likely I will not be able to get to the Q part, but a lot of the interesting information is, well, the Q part is extremely interesting as well, but a lot of the talk, most of this talk will focus on this prime part, whereas the prime varies. Yeah, all right. So this is maybe a different exposition from Motivic cohomology that you're used to, even if you're an expert. And according to Georg, there are a lot of experts in the audience, so I hope it's not too boring. So I'm going to begin live by talking about some predecessor of Motivic cohomology, namely this so-called Bloch-August theory. So this Motivic cohomology is defined across all fields, and one cohomology theory that's kind of defined across all fields that's already there for you is étale cohomology. So for now, let me talk about the case when the coefficient is invertible in K. So this M is an integer which is invertible in K, and X is a smooth scheme. Okay. So out of this data, I can produce for you this chain complex concentrated in cohomologically non-negative degrees, which computes étale cohomology. So in particular, the ith cohomology of this complex is just the ith cohomology, étale cohomology of X with coefficients in this mu n tensor J, which let me remind you is the sheaf of m roots of 1, and I just twist by j. Okay. So this is a familiar looking theory to a lot of people. And you can ask, can I produce algebraic cycles? Maybe this should really be a question. So since Motivic Cohomology is a way to sort of enhance algebraic cycles, you can ask, is there a way to produce algebraic cycles out of étale cohomology? So here's one attempt to do it in the 70s by Bloch and Ilges. So what you can look at is this morphism of sites from the étale to the Zariski site. And then you can take the derived push forward of this mu m tensor J. So note that this mu m tensor J is a discrete sheaf. So this is discrete. But if I take the derived push forward from étale to Zariski, then what you produce on an open, so this U is just an open inside X, you produce this cochain complex, which computes the étale cohomology of U with coefficients in mu m tensor J. So in general, this is this has information in higher cohomological degrees and need not be discrete anymore. So one way to understand the situation once you have a push forward between sites is to look at the change of site spectral sequence. So this is the change of site spectral sequence, whose E2 page looks like HI étale X with coefficients in HQ mu m tensor J. So this is the Zariski sheafification, right, of the functor that sends U to the Qth étale cohomology of U with coefficients in mu m tensor J.
Which should be H.
Sorry? J. Yeah, maybe. Yeah, this should be P. Thank you. So HPX, HQ, mu m tensor J, and J is fixed.
HP is Zariski.
Thank you. Yes, it's definitely Zariski. Yes. So the E2 page has some Zariski cohomology, and it converges to HP plus Q étale of X mu m tensor J. Okay. All right, so the spectral sequence looks like this. So yeah, again, J is fixed, and I'm going to shorthand the Zariski cohomology groups as HPQ. All right, so here's how the spectral sequence looks like. You see, you have this H0, H10, H20, so the degree 0 piece is just lying right here. And then this is the degree 1 piece, and the differential goes like that. So because the Zariski cohomology, the cohomological dimension of the Zariski site is bounded above by the cool dimension, this row goes all the way down, go all the way up to the dimension of X. So to the right here is all 0. So you can ask, what is the spread of the spectral sequence as you go up? So because we are looking at the vanishing of this Zariski sheafification of the étale cohomology sheaves, is going to be bounded above by the cohomological dimension of K, which is something that étale cohomology is sensitive to, plus the dimension of X. So you don't see the twice dimension of X because we're only looking at affines. This is a version of the Andreotti-Frankel theorem of étale cohomology. So it goes all the way up to cohomological dimension plus maybe this should really be M. Cohomological dimension of the field plus the Zariski, the cool dimension of X. All right, so this is a spectral sequence which is very active and very live. There's like a lot of these differentials, but we can already make a couple of remarks. So we note that étale cohomology is manifestly a kind of topological invariant. So there's this Artin comparison theorem, which over C relates this Zariski étale cohomology to singular cohomology of the C points of X. And the cycles, which is the thing that we want to produce, is actually hidden within the E2 page. So this is the Zariski cohomology with coefficients HQ is kind of the thing which is more related to cycles. And in fact, this is one of the themes of this whole series of lectures, is that we want to extract information about some E2 page from the E infinity page. And a lot of this development in trying to understand Motivic cohomology singular schemes is really about saying something about the E2 page of a spectral sequence, knowing what the infinity page should really be. Or rather, not even the infinity page, the abutments. Yeah. Right. So what you want to do if you want to access the E2 page via the E infinity page is to eliminate as many terms in the E2 page as possible. So let me explain that. Right. Okay. Sorry. Before I explain that, let me just get you oriented with some examples. So suppose for simplicity, I'm working over an algebraically closed field. So if X is projective, then what you get is the following. So HDD is the only term in the spectral sequence that survives. So HDD is the same thing as H2D et al. Of X with coefficients in mu m tensor J. This does not require X to be projective. But if X is projective, then it's the top cohomology and it becomes Z mod M. Okay, so there's some information that you learn that these Zariski cohomology, if coefficient in HD is exactly Z mod M. That's quite nice. But in general, these H0J are quite subtle. So in fact, Hij, as I and J varies. So for as an example, H0J are birational invariants, which are called unramified cohomology and has been studied by many birational geometers. So there's a whole digression, which I don't want to get into, but I kind of implore you to Google this theory, and it's a very fascinating and useful theory that has been used to study information about algebraic cycles on X. Okay. So what Bloch-August did in order to produce algebraic cycles out of this picture is to prove the following vanishing result. So when P is greater than Q, these groups vanish. So this is what they proved back in 1974. So this is really ancient origins, if you like. Okay. So what does this theorem say? Well, you see, so, one second. Yeah, okay. Yeah, so what this theorem says is that whenever I, let me just use some different color. Maybe I use red. Oh, no, I use black. So this is the spectral sequence. I just copied and pasted it. And what happens here is that these groups, for example, is zero because 1 is greater than 0. So all of these things all disappear. And in fact, this H2 also disappears. And anything right here just disappears. Right? This is what the Bloch-August theorem says. All this triangle, which kind of just vanishes. So I wanna look at a particular example when I'm again over an algebraically closed field and the dimension of X is 2, so it's just a surface. And for simplicity, I wanna work with L, just a single prime, and I just want to trivialize the Tate twist. Okay, I'm allowed to do because I'm over an algebraically closed field. So this Bloch-August theory kills all of these groups, and because I'm a surface and I'm over an algebraically closed field, the only interesting part of the spectral sequence is exactly just this. So maybe I would just want to redraw it. So the spectral sequence that's left over looks like this. So there's the top row, there's the second line, and that's the bottom line. Okay, so the new information that you get out of this Bloch-August vanishing theorem is that H12 is the thing that's exactly H3 et al. X Z mod L or Z L. Yeah, you see, usually like without this Bloch-August theorem, there's something here that contributes to H3, and that would have been like kind of confusing. But H12, which is, let me remind you, what you want to access is this, is really the E2 page. It's really isomorphic to the infinity page already. Right, so in the previous slide, we saw that H22 is et al. Cohomology. That's not so surprising, but now we get new information that is H12 is also et al. Cohomology. So what you learn from this perspective is that I can try to compute H12 in terms of something else. Okay, so I'm going to assume the X is projective. It's always assumed to be smooth. And when that's the case, I have I've converted my coefficients here to be QL mod ZL. So this is just the co-limit as L to the nu varies as nu goes to infinity. So this collects all the L torsion inside this H12, and this isomorphism, maybe I can put a mu here, really, is compatible as this nu varies. So this H12 is really just H3 et al. With coefficients in QL mod ZL. So this is just collecting all the L torsion that's available. Then when that happens, what you get, if you're projective, you can appeal to Poincare duality. And you see what you get is you get H1 et al. Of X with coefficients in ZL dualized. Okay, so this is some Poincare dual. And by definition, the duality means this is just this is H1 et al. X ZL, but there's another name for it, which is the Tate module of the Picard group of X. That's what H1 et al. Is. And this is telling you that H1 Zariski is the dual, or the Poincare dual, of the L-adic Tate module of the Picard group. And there's another name for this, namely the K points of the Albanese variety of X. So this is the Albanese variety, which, if you're not familiar, it's the universal abelian variety under X. So in particular, you see kind of maybe surprising result that when X is projective and a surface, so I'm still dim2, that this H1 is isomorphic to the K points of a certain variety. It's like kind of new information. And what this leads you is the following theorem due to Reutemann. So Reutemann proved this theorem way before 74, but he used more analytic methods. But Bloch and Milne used this vanishing results, or the Bloch-August perspective, to reprove this result. And the point is, so I'm not going to tell you how this is proved, but what you get is the following picture. So you have this Albanese variety, and you look at the L torsion. So I should have said really the L torsion, or the L infinity torsion, since I'm just concentrated at L. Yeah, so the L torsion of this Albanese is isomorphic to this H12. And what this buys you is that there exists a map from this H12 into the Chow groups of zero cycles on X, L infinity torsion. Okay, so this map is not quite easy to define. I mean, you need some more things, and this map turns out to be surjective. So for experts in the room, this is you use the fact that Chow 0 is H2 Zariski X K Milnor 2 L torsion. And you can spend the next couple of minutes thinking about what this map is and why this is surjective. So so this is some kind of boxed-in map. Let me caution that, like, I'm not saying that this kind of makes the proof extremely easy. There's still some steps to be done, but it kind of produces a certain interesting non-trivial map from H1 to Chow 0. And this map star really follows, well, nowadays from the Merkurjev-Suslin theorem or the Bloch-Harter theorem, but in this particular case, it's much easier. This is what Bloch does in his book on algebraic cycles. And Reutemann's theorem is the assertion that this map is in fact an isomorphism always, if for any X which is smooth projective any dimension. So I only told you what happens for a surface, but there's some standard reductions for you to reduce from smooth projective varieties of any dimension to a surface.
So the Bloch-Harter is for the P part or for
the L part? The P part and the L part. So for the P part, you have to use, well, I mean, Geisler-Levine, if you like, or Bloch-Harter-Gaber. Bloch-Harter and yourself.
But what is the Bloch-Harter here?
Oh, I need to relate étale cohomology to Milnor K-theory. So you can use Merkurjev-Suslin.
You don't need the full conjecture. You need,
no.
And also you forgot to have some K-twist here in the H2. It's not completely in the source. You forgot some K-twist.
Yeah. Oh, yeah. It should be 2 here. Yeah. Is that better? Yeah.
So the star is an isomorphism for smooth projective varieties?
Star is a surjection for smooth projective varieties.
But the two other arrows are isomorphic, right?
Yeah, exactly. So what you learn is that this is okay. So you want to prove that this is surjective. So you want to prove this is an isomorphism. It's not so hard to prove this is injective. And then what you end up proving is that there is a surjection backwards via this map. So that's the whole strategy. Yeah. And so I'm about to state the theorem. So the theorem is that whenever X is, this is due to Weibel, but Bloch and Milne reproved it. So Bloch is when M is invertible or the torsion is invertible in the base field, and Milne is when you are at the characteristic. So in this situation, when X is smooth projective over a field and you're algebraically close, then the torsion in 0 cycles of X is exactly isomorphic to the K points, the torsion of the Albanese variety of X, and take the K points. I mean, torsion and the K points, rather. Excuse me. Yeah, so Bloch is when the torsion is in the field and Milne is at P infinity torsion. So this was for a long time, like kind of the main tool that you use to study torsion inside 0 cycles of X, which is a very interesting and very powerful invariant about X. And it really uses this a deep analysis of this spectral sequence going from Zariski cohomology into étale cohomology.
And Weibel had his geometric proof, as far as I understand.
That's correct, yeah.
And his proof is this proof also is in general, or just in he proved it for all K and all torsion, or some?
Yeah, Weibel does it generally as well. That's right. Yeah. Right. So I want to tell you the idea of the proof of this Bloch-August theorem. Then, yeah, so there's some really deep geometric information being hidden kind of in this whole picture. And I'm going to try to demystify it by telling you how the proof kind of goes, okay? So suppose I have an open inside X. X again is smooth over a field. And let's say X is irreducible so that there is a generic point. So this is like the function field of X. So then I can produce a complex called the Gersten complex. Okay. So there's a cochain complex which depends on U. So it's functorial inside U. And there is this second variable, which is the sheaf that you input. So you can imagine a more general way that you can produce this complex where you put a random sheaf here, F. Okay. So the zero term of this complex is the étale cohomology. The étale cohomology of the function field of X valued in this mu m tensor J. That's the zero term of the complex. And then the first term of the complex is a direct sum across all codimension 1 points. So this is codim 1 points of X. Yeah, so and you have étale cohomology of the residue field. So this is the residue field at the point. But now I'm twisting. So there's Q minus 1 here, and there's J minus 1. And then there's Q minus 2 here, and then J minus 2, and you're looking at codimension 2. And in general, you have codimension P, and then you have Q minus P and J minus P. And dot, 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 and so on. So there are these boundary maps that connects all these complexes, and it's some kind of residue map. So I will not go really into details, but you should think of them as some kind of residue maps. And you have this cochain complex, and notice that as soon as this Q minus P is negative, this complex stops, right? Since there's no negative cohomology. Okay, and the main theorem of Bloch-August, what they actually prove is that this is a Flass resolution of the sheaf HQ mu m tensor J. Okay, so there's this length P, or a resolution that goes at most to Q minus P less than Q minus P non-negative. There's that chain complex which resolves this Zariski sheaf, and because of the terms of these complexes are basically just skyscraper sheaves. This is Flask. Okay, sorry, I kind of made a mistake here. So since I put a U right here, I'm supposed to put a U inside all these terms. So I'm looking at this codimension P points, codimension P minus 1 points, and so on of U. So that's the general pattern.
Are there any assumptions in the base field?
Sorry?
Are there any assumptions in the base?
So for now, 1 over m is in K, which is my standing assumption throughout.
And that's it.
Yeah, that's it. That's it. Okay, so one corollary that you get, right? So let me just say that this immediately proves it because there's no negative cohomology. So this vanishing of Q minus P less than 0 is explained by the length of this complex, since you can just take this complex, evaluate on X, and that's a chain complex that's capable of computing étale cohomology. And therefore, you get the vanishing range that I stated at the beginning a few slides ago. But you get more. You learn about the following corollary, that when I put this number to be J, this number to be J, and this number to be J, so you get this triple J thing, you get the Jth Chow group of X tensor Z mod M. Okay, so let's see how that works. So if I want to compute HJJ of this cohomology, then I'm just merely looking at this section of the complex. Okay, so this is codimension J plus 1 points, and this is first étale cohomology, and this is codimension J points and 0th étale cohomology. So by Hilbert theorem 90, H1 is nothing but Kx cross modulo Kx cross to the M. Okay. And this H0, there's no more T-twist, and it's just Z mod M. Constant. So this is, if I were to put a Z right here, if I were to put a Z in this spot, then I'm just looking at the free abelian group generated by codimension J cycles. But now I put a mod M, so it's like the mod M version of that, Z mod M version of that. And this is this equivalence relation that's imposed by by taking the kernel mod image of this complex is nothing but rational equivalence. So you should think about this as some kind of cellular chain complex. So you have like codimension 0 points, codimension 1 points, and so on. So that's just a picture that I just drew randomly. Okay, but anyway, because I'm really just looking at this little chain complex right here, you see that it really coincides with child groups of codimensions J cycles of X tensor with Z mod M. Yeah. So algebraic cycles is really produced out of this HJ, out of evaluating this Zariski cohomology at a certain spot. Okay, so that's kind of nice. This Bloch-August machinery not only produces for you vanishing results, but also produces for you algebraic cycles at the very top degree of this Zariski cohomology groups. Okay, so then yeah, so that's quite nice. So I just redo the spectral sequence. And you see that you have vanishing in this spots, you have all these things vanishing, which is very nice. But you note that in the E2 page of this spectral sequence, this Chow groups, which lies inside this line, so we highlight it. So it appears here, and so on. Right? The Chow groups that appear in this line in general need not survive the spectral sequence. So there's these differentials that goes inside here that may kill the terms inside this diagonal. This is what happens. And in fact, it does happen because we do know a posteriori that Chow groups of codimension J cycles need not surject onto étale cohomology. So there's a map here, which is a cycle class map, which can be interpreted as some H map in the spectral sequence. And it goes into H2J étale, mu M tensor J, and this need not surject. There are various counterexamples to this. And so this spectral sequence, this E2 term, this thing which is discovered inside the E2 term of this spectral sequence did not survive the spectral sequence. And so étale cohomology is not really the thing that you want in order to produce algebraic cycles. Okay, so the solution to this is kind of naive. Let me propose for you a solution to this problem of producing algebraic cycles. What I just do is I just cut, right? So there's a spectral sequence, there's these differentials that I do not necessarily like because I want to see cycles. I just cut here. So let me do that. So ZMJ mode, I'm going to define it as the truncation in Vj, and this truncation is Zariski local. There is some Zariski local truncation of the derived push forward of mu m tensor J. Yeah. That's all. That's it. So that's my definition of motivic cohomology. Is that I take this mu m sheaves, which are just discrete abelian sheaves. I push it forward to the Zariski site. Maybe that highlighter is not very good. Yeah, so I take this discrete sheaf. I push forward to the Zariski site, and then I just truncate. Just cut. Yeah. So there's a spectral sequence whose E2 page is some cohomology groups computing the hypercohomology of this complex. And the spectral sequence is just what you get by just truncating this. Yeah, so this is like dimension 2, say I just truncate above this degree. Why not? Okay. Any questions about this proposal for what motivic cohomology is? Yeah, well, the experts should complain about this, like, oh, like, I guess I'm hiding a very deep theorem here, but after the fact, this is just something I'm kind of allowed to do. Just take the truncation of this derived push forward. Okay, fine. So from this formula from this truncation formula, I can read off certain information. Sorry. So let me just for notation's sake, I'm just gonna say hi mot x z mod mj. I'm just going to define this to be the ith cohomology of this complex evaluated on X itself. Okay, so I just take the global sections of this complex, and I just take the ith cohomology group, and that's like what my motivic cohomology is. Okay. Nothing but that. Okay, so here's a proposition. So if I look at the top cohomology 2j, j of this complex, I immediately get Chow groups, right? And I get this via the identification with this Hj Zariski of X, Hj mu m tensor J. Yeah, because there's no differential that can come in and out of this. It will just survive the spectral sequence, right? And it just immediately gives me that the 2j, j part is just the Chow groups of codimension 2 cycle. That's something I can do. So you see, if because of the spectral sequence again, when p is greater than twice the dimension of X, it disappears. But it also disappears when p is greater than q plus dim X. So this is the kind of vanishing range that I can produce immediately out of this maneuver and examining the truncated version of this Bloch-Ruger spectral sequence. Okay, which is two very nice properties that I really want out of motivic cohomology. And when X is the union of two opens, so U and V are opens, I claim there is a homotypic Cartesian square of this following form. Okay, so this is homotypic Cartesian. So what I'm using right here is really the fact that I've done Zariski truncation. So there's something to be proved. So let me go back to this formula. If I had taken this truncation just naively, then I will not necessarily get the Zariski descent property, but because I've taken the Zariski truncation, this truncation is done in a sheaf theoretic manner, I get this Zariski excision square. Okay. So that's like one of the things that I want out of motivic cohomology. And in particular, I get a long X sequence where you have this at the bottom, you get H2j, j. So it becomes 0 since there's H2j plus 1 here, but that's 0. And these things are the Chow groups. So this is the Chow j of X. Well, now I only look at mod m coefficients, or I tensor with mod m. So I have Chow j of U tensor Z mod m, direct sign Chow groups of V tensor Z mod m, mapping to Chow j of U intersect V tensor Z mod m. And that's surjective. So this bottom row coincides with this Chow group SX sequence that's more familiar, but there is a differential, there is a connecting homomorphism that wraps around right here. And in general, you have these rows where you have X and this U and V opens and this intersection. And they're connecting homomorphisms that connects various values of P. Okay, this is what you obtain out of this Zariski open excision. It's like one of the things that I require out of the theory of motivic cohomology. So let me discuss in the next kind of 15 minutes or so what happens at a prime P. In some sense, this is really a recasting of the, in classical terms, of syntomic cohomology, which is the topic of the Arbeitsgemeinschaft. So hopefully this kind of lecture will interact well with what's going on in the rest of the program. So in this situation, you have a smooth scheme over FP for simplicity. So you can put any perfect field if you want of characteristic P, but let me stick to FP. Then what you obtain is the following picture. So you have this GM, which I consider as a Zariski sheaf of abelian groups on the Zariski side of X, or rather, maybe I'm gonna do it like this. I'm gonna put a étale sheaf of abelian groups on the étale side of X. Yep. So you have this GM, and there's a map from GM into this sheaf of differential forms of X, thought of as an étale sheaf of abelian groups. So this D-log map does the following. So you have a bunch of units, F1, tensor, ... tensor, J. Those are units inside an open, if you like. This maps to D-log. So D-log is dF1 over F1, as you expect, and then you just wedge them together. dFj over Fj. Okay, so this is a morphism of étale sheaves. And what you can do is you look at the étale sheaf image. So this omega j x log, okay, is going to be defined as the étale sheafification of the image of D log, thought of as a sheaf of as an étale sheaf of abelian groups on X. Okay, so I just look at the image or the étale sheaf of the étale sheafification of the image of this D log map. And then what you get is the sheaves called omega j log. So as an example, when A is a local ring, well, I mean, since you're in the étale setting, maybe this thing to say is strictly Henzelian local ring, but it's true more generally. This D log map witnesses an identification between A cross mod A cross times P. So this is really GM mod P of GM evaluated at A. Right, so this is the quotient as an abelian sheaf, and you evaluate on A, and when A is a regular local ring, well, when A is like, for example, the local ring of a smooth point of X, you get that this omega one A log is isomorphic to this quotient. So it's some kind of it's some avatar for you, mod P, if you like, of A. Yeah, so the basic idea, which has been proposed by many people, is that this omega jx log is really the correct version of omega P tensor J. It's really the correct analog of mod P tensor J whenever I'm at a characteristic. Yeah, so note that the literal mu P tensor J étale sheaves doesn't behave quite well. So because of lack of time, let me just explain why this omega jx log is like the correct thing in some sense, as opposed to telling you why this mu P tensor. Okay. So sorry?
There is a shift. So it's like the direct image of mu P from the flat to the étale side.
Yeah, right.
There's a shift, and then you think that there is some ideal site on which this lives, and then the direct image would be with a shift. Okay. This is what Milnor said.
Thank you. You should put a J. You should put a shift there. Yes, I'll talk about the shift very soon. Yeah, thank you, Oprah. So So here's one way why this is a very reasonable perspective. So suppose X is now over FP bar, so it's a smooth scheme over FP bar. You can replay the same story. Then there is some perfect pairing between HI et al. X omega j log and HI d minus I d minus j of this omega j log et al. Cohomology. And it's a perfect pairing that goes into HD omega d log. And there is a trace homomorphism that Milnor wrote down that witnesses an isomorphism between this D, D et al. Cohomology with Z mod P. And we saw that this duality in et al. Cohomology is an important ingredient in proving Weibel's theorem. And Milnor's idea to prove Weibel's theorem is exactly to replay the same strategy, but replace this Poincare duality in et al. Cohomology with this duality with et al. Cohomology and this omega j log sheaves. So he proved this Poincare duality in this omega j log sheaves in order to prove Weibel's theorem, in order to give his proof of Weibel's theorem at the prime P, which is like a genuinely new thing, I think. I mean, like Weibel was over characteristic 0, and this is like really a new phenomenon, if you like.
But the other duality of the finite fields, this was explained in another talk. The other duality in the naive sense for a finite field, it would be plus 1. But here you need the duality in some derived sense of a perfect psi, which is not less than not exactly what you said.
Sorry, but I think this duality is okay. Just over FP bar. No.
Okay, to look up. I remember that there is a derived thing with the perfect psi.
Right, absolutely.
Different components of it's not so like things with ordinary varieties. It depends, like for kind of ordinary in the sense of log Cartwright. So,
right.
But in general, okay, I don't remember exactly, but it's not.
There is a version.
It's a continuous. There's a continuous part, which is and this continuous part is like an algebraic group.
Yeah.
You cannot have a pairing for algebraic group over FP bar. The point of an algebraic group cannot pair with. You cannot have a non-trivial pairings for. Doesn't seem to.
Maybe we can discuss this afterwards.
Okay.
Yeah. So, but he does use a duality like this for FP bar to prove this Weibel's theorem. And there's also this analog of the Gersten story as told by Go and Sua, where they do the same kind of game, but now with this omega j log sheaves. So again, you still have this projection from the et al. To Zariski site, so you can project this omega log sheaves from the et al. To Zariski site. So I don't take the direct push forward. I just look at a single sheaf now, and so you have the complex of which has similar terms. So the complex starts here. You have the Q omega j log omega Q log of the generic point or fraction field of X, and then this goes codimension 1, and then you subtract 1 here, and then goes to minus P, and again it stops whenever Q minus P is less than 0, and then you put a P here. P, codimension P, and again provides a fast resolution computing Zariski cohomology of pi lower star omega Q log. Okay, and what you get is that you get HQ Zariski of X pi lower star omega Q log is isomorphic to Chow Q of X tensor Z mod P. Okay, so you have the same story where you reproduced the theory of algebraic cycles on X via this omega j log stuff. Yeah. So you see that it kind of it's a pretty good analogy up to a shift that that Ofer mentioned of this mu p tensor J objects. Okay, so I'm going to define Motivic cohomology at the prime p via the following truncation. So I'm going to use the same kind of formula. So you take R pi lower star, again, where pi is the same push forward. And then I'm going to take omega J log, but do the shift. So this minus J. Okay. And then I'm going to do the same truncation, tau less than equals to J. So whiskey. Right. So it's like exactly the same type of formula. And then but this is when J equals to 1, and when J equals to 0, okay, I just put FP. Why not? It's just the Zariski sheaf FP. The constant sheaf FP. Okay, so Motivic cohomology in degree 0 is always just Zariski cohomology valued in the constant sheaf. So because I've done this truncation and I've done this shift, okay, then what I get is this isomorphism, that this Motivic cohomology with this at I plus J is just the Zariski cohomology of this particular sheaf. Okay, like this sheaf doesn't start being interesting up until degree cohomological degree J, right? So so this Motivic cohomology at a prime P is nothing but Zariski cohomology of a single sheaf, just like that. When J greater than equals to 1, of course, it's the same when J equals to 0, but it's just the Zariski cohomology of the constant sheaf. So here's a non-trivial fact. So instead of taking the étal image, which is what I did right here, I could have taken the Zariski image, right? This GM tensor J mapping to omega J log. I can take the Zariski version of the image, and this pi lower star, in general, there is an injection like right here, but because of results due to Bloch-Hartleb-Gaber and Moritz-Kurtz, this map is in fact also surjective, and the Zariski image is the same thing as the étal image. That's a fact. So you can really replace this pi lower star with omega J log Zariski. So you can see this in a paper of Matthews, where this was kind of cited as a Folkvard theorem. Okay, so the P version and the L version of Motivic cohomology has kind of the same formula, same kind of recipe. You push forward some sheaf from the étal side, and then you just truncate. Like kind of just the same. Okay, so let me explain that. I don't want to go into too much details. So when R is greater than 1, well, I've showed you what happens when R equals to 1, basically. But anyway, for any R which is greater than equals to 1, there this WR version of this omega J. Okay, so you can put a WR right here, which will remind you of the bit vectors. So these are sheaves which are Z mod P to the R modules. Yeah. Is there a question?
Not yet.
Okay, yeah, please feel free to bring them. Just feel free to ask questions. So this is WR version of this omega J log sheaves. Okay, and in general, including R equals to 1 is the kernel of this WR omega J log, which are extracted from the Drummond complex, mapping into WR omega J of X, modulo this image of D via 1 minus C inverse. So hopefully this will be talked about in the Arbeitsgemeinschaft. This is really a formula for WR omega J log in terms of some for some Frobenius eigenpiece, if you like. So it's some kind of Frobenius eigenpiece. Since I should be thinking about this Katia operator as some Frobenius. Okay, and so this thing will appear in the Arbeitsgemeinschaft as Z mod P to RJ sin, and it's equivalent to a shift of this WR omega JX log when X is smooth over FP. Okay. So all of this is to say that this object will be discussed again and again throughout this summer school. So hopefully people will get kind of comfortable with this omega J log, maybe even more comfortable with this than étal cohomology itself. Okay, good. So that's the story with the P part and the L part. And I'm going to briefly talk about the rational story. But before that, is there any questions from the audience?
Why the two definition for R equals to 1 is the same?
Sorry?
For R equals to 1, why the two definition are the same?
Oh well, you have to prove it. It's not immediate. Yeah. So I'll leave it at that. I'll leave it to the Algebraic Gemeinschaft to sort of kind of explain this phenomenon. That on the one hand you can talk about the 1 minus C inverse kernel. On the other hand, you can talk about the étale sheaf generated by, or the Zariski sheaf generated by the image of D log. So two different perspectives. Anything else? Okay, this is apparently a teaching technique to kind of wait for, I don't know, 1 minute or 30 seconds. All right. So I want to talk about rational motivic cohomology kind of briefly. So Bailenson had a vision that motivic cohomology should be whatever is the graded piece of a filtration on K-theory. So in particular, when everything is rationalized, it should be the graded piece of some filtration on higher K-theory. Okay. So you can kind of define that. You can kind of find right. So the rational story is a bit older, and as soon as you have the Adams operations, which are right here, you can really define motivic cohomology. So in characteristic 0, when m is greater than or equals to 2, you can define this psi m self maps, which is a map, which is a self map of the rational K-theory spectra. So maybe I stick myself to the smooth situation for now, and you have the psi m maps, which are just Adams operations. On rational K-theory. Okay, and what you can do once you have this rational K-theory as spectra. Yeah, so once you have this self-map of spectra, you can define QJ mode simply as the m to the j eigenpiece. So this is the m to the j eigenspectrum. Of rational K-theory up to a shift. Okay. So what you want to prove after you define it like this is that it's independent of m. Just that this QJ mode is defined, so this left-hand side has no reference to m, and you have to prove that this thing is independent of m by just you have to prove that. I'm not going to explain how that works, but it is true that this eigenpiece is independent of m. But in characteristic P, there's something better, namely the Frobenius. That's a very friendly object, very friendly operation. Again, this Frobenius that has sense x to the p, and it's functorial for in an appropriate sense for FP schemes. So there's this Frobenius endomorphism on rational K-theory in characteristic P, and you declare this QJ mode to be the P to the J eigenspectra up to a shift.
Is it psi p in this case?
Is it what?
Psi p.
It is, yes. If you had produced the Adams operation, it is exactly psi p. Absolutely. Yeah. So that's what you declare.
There's some power of p in front, isn't there?
What?
Maybe on the nth K group, it's p to the n psi p.
Yeah, on the nth K group, it acts as. Yeah, so on psi p, yeah, I'm not gonna remember this. So okay, I'm not gonna remember.
Frobenius is p to the n times, so that doesn't matter.
Yeah, Frobenius is p to the n on the nth K group.
So times psi p.
Times psi p. Yes, is that like this? Yeah, that's right. Yeah.
I'm not so sure anymore. I respect any claim. It doesn't look like anymore. No, it's P to the N lambda P. P to the N lambda P.
Yeah.
Right. You better leave what you got actually. Right.
Okay, let me let me skip that. But I'm just going to stick with the Frobenius. That's just a much happier thing than the Adams operations, as Matthew and I have been struggling with. Yeah. Okay. So yeah, so that's what you can do. I'm just going to declare it as some eigenspectral. So there's some gluing map. Okay, so there's some gluing map from this QJ mode objects into the product of this ZPJ, but it's not quite obvious how you construct such a gluing map. There's more theory. So this is written up in Szynski and de Vries' book. I think there are possibly many ways to do this, but the reference that I like is this triangular category of motives book by Szynski and de Vries. So they establish universal properties of this QJ mode as J varies. So it assembles into something called a motivic spectrum, and there's a universal property of the resulting motivic spectrum that you produce out of this QJ mode. And this universal property lets you map into this product. But in order to do that, you need to establish certain properties of this ZPJ mode. So this as J varies, this ZPJ mode, you need to verify two things. You need to produce A1 and you need to verify A1 invariance and P1 bundle formula. But let me kind of mention that a bit. So you need to know that ZPJ modes, which I've declared as this truncation, has the following property that there is an equivalence between ZPJ mode and ZPJ mode X times A1. So that's the pullback map, pi upper star, that is an equivalence. So that's A1 invariance. And two, and this is more important, and this will be discussed in Riome's series of lectures, that there is this C1 map from PIC into a H2 mode blank P1. So let me just look for it a second. I think it's like, it's there. So there's a transformation from the Picard group of X into H2 mode X ZP1, and it yields the following isomorphisms. So let me write this as a theorem. Okay, for any P and J greater than or equals to 0, there's an isomorphism between this Motivic Cohomology of X and Motivic Cohomology of X times A1. So there's A1 invariance. And there exists this theory of first-gen class from pic of X into ZP1 mode X. And for any J greater than or equals to 1, you can establish the following equivalence of complexes. So first, you take this ZJ mode X and map it into ZJ mode P1 times X by just pullback. So let's just pull back. Or you can take this shifted version. So you have ZP. So there's all still P. You can take this ZPJ minus 1. You have this ZPJ minus 1 shifted by minus 2. So you can map it into ZPJ minus 1 mode shifted by minus 2 of X times P1. And then you can cup it with C1 O minus 1. Right, this is O minus 1 sheaf inside P1, and you can cup it there. And these two maps added together, right? So you take the direction of these two maps and isomorphism. So in this treatment of motivic cohomology, which is handcrafted, these two theorems are very hard. Right. So this proof will require to take us to further afield. And for example, this isomorphism can be established from the formalism of sheaves with transfers in motivic cohomology. And you can also use that to establish this second isomorphism. But maybe the best thing to say is that the Bloch-Kato theorems, or the isomorphism that's established by Rose and Voivodsky, immediately gives you these two theorems. It's like kind of repackaged into these two theorems, which are kind of not really obvious from this handcrafted perspective, but it's true nonetheless. Right. So once you've established this A1 invariance and this P1 bundle formula, what you can produce is this universal map from QJ mode into this product of this into this rationalized product by a universal property that's established by Szynski and de Vries. Okay. So so in any treatment of motivic cohomology, there are non-trivial things. So if I started life using Bloch-Sacco complex, or maybe Voivodsky's version of motivic cohomology out of DM, you still need to produce properties like this. And in particular, it's not really obvious what they mean. You know, like the block spiral complex is something that's like kind of concrete, but it's kind of difficult to compute. It's kind of hard to relate it to étale cohomology. I mean, that's like the whole point of Bloch-Hattow's conjecture or the Rose-Voivodsky theorem. But from like starting out with like just étale cohomology, it's kind of hard to produce A1 invariants. It's kind of hard to prove A1 invariants and P1 bundle formula, but at least at the beginning, you sort of know how these complexes look like, or like you kind of have a handle on these complexes. So I mean, take your pick. I pick one lane, and that's the lane I picked. And yeah, so from that perspective, this becomes kind of very hard theorems, but nonetheless true. So here's a harder theorem when K is over Fp and Q, and so I'm going to summarize in a precise way exactly this Motivic spectral sequence story. So when K is a prime field, there exists this Motivic filtration. There exists a filtration on K-theory called fill star modes, functorial on essentially smooth schemes over K. So this filtration is multiplicative and is infinity in a precise way. It's an exhaustive filtration, is also complete. Okay. And this Gerst star modes is identified with this Motivic complexes, which is handcrafted. That's like the content of the Bloch-Hattow isomorphisms. And this D star mode enjoys P1 bundle formulas, or in fact, PN bundle formulas. So the version for projective spaces of higher dimension, A1 invariant, and in fact, not only Zariski sheaves, but also Nesterenko sheaves. So Zariski locally, this Z mod J is concentrated up to degree J, which gives rise to all these vanishing isomorphisms, not vanishing results in Motivic cohomology. And there's one more thing which is extremely important, but I don't have time to discuss. Namely, when these two things are J, and A is a local ring, A is local, essentially smooth K algebra, it identifies with Milnor K-theory in degree J. Okay. So this is the theorem. This is the basic kind of design requirement for Motivic cohomology, and it's a theorem of many people. I'm gonna kind of comment. I'm gonna make a comment on how you would produce this theorem, or how you would prove this theorem by. Well, I'm gonna attribute. I'm gonna make some comments on this proof and give attributions along the way. So how you would prove this theorem if you start out with Motivic cohomology defined as this handcrafted version is to proceed in the following manner. So first you use the size filtration in stable Motivic homotopy theory, and this is something that will be discussed in this lecture after this by Hannah. So this is Morrow Voivodsky. And this filtration is automatically going to be multiplicative by formal reasons, and it's going to be exhaustive again by formal reasons. So then you need to compare this construction to other known models of Motivic cohomology. So you need to know that this size filtration, that the slices of the size filtration, KGL. So this is something that will be hopefully kind of discussed in the next lecture, is equivalent to this Motivic spectra produced out of this handcrafted Motivic cohomology. And to do that, well, you need, of course, Voivodsky's work. You need a moving lemma due to Mark Levine, started out by Spencer Bloch. Of course, you need this compatibility of Adams operations, which is I'm going to attribute to Soulé for this rational stuff, but within the context of stable Motivic homotopy theory, is really work of Joël Rioux. Yeah, so there's no shortcut really, but this is just the story kind of repackaged in a different light. So I think I'm exactly on time. I think I'll stop there and take questions.
Questions?
What do you say? What you wrote need? Can you spell out what you have written in the line before the last? Need as G.
I can't hear you. Sorry.
So need what you wrote the line above the last.
Yes.
No.
Need SJKGL computation for slices.
Exactly. So what you want to do out of this formalism of stable motivic homotypic theory, you get some filtration called the slice filtration on KGL, where KGL is this motivic spectrum representing algebraic K-theory, which I think will be kind of discussed maybe in the next talk. And then you just this SJKGL are the graded pieces of the slices, and you need to compute the graded pieces of the slices. And you need to, by compute, relay that to the thing that I've already constructed, and you need basically everything else. You need all the theorems that everybody has proved in order to identify the slices with this handcrafted motivic homology. So in the notes that I posted on my website, I kind of sketched out how this works with appropriate attributions and references.
Other questions?
Could you go back to that that part about the torsion in the Albanese variety?
Sure. This one.
Yeah. So other known results. So in the end, you get the computation that compares the points of the Albanese variety with 0 cycles.
Yes.
Are there any geometric models for torsion in higher chunk groups? Besides,
I don't know. I think people like Thomas Geisler has some paper kind of pointing out which parts of motivic homology or maybe étale motivic homology which are representable by some scheme. I think Matthew knows this better. But in general, I think it's like kind of complicated. Charles zero is like somehow already a big achievement that it's representable by the K points of a Billion variety.
Matthew shake his head. Probably he doesn't know.
So
but maybe Federico also knows. There are people in the audience.
Just I want to remark on a formula that was probably not right. There was a formula for the log the round-weight differentials in terms of 1 minus C inverse, and C inverse comes from the operator F, which is defined on the infinite the round-weight. And so on the infinite level, as far as I remember from Visual Z, you get just 1 minus F, gives you on the taro, gives you the inverse limit of the log the round-weight. And so on finite level, I think you don't get what you have written with D, but it's just a small, I don't remember where is the reference, but instead of the D of something, maybe you have some D with some power of the Shibu. Anyway, it's not exactly what you have written.
Oh, but I only wrote level. Oh, yeah, maybe.
It's not modulo D, but modulo something with, as far as I remember, something slightly more. Instead of D of WR, you need maybe some D Shibu.
Yeah.
With power
It would be dv to the r, dv to the r of omega x.
To r minus 1.
And no omega, no wr.
Yeah. Okay. Yes. Sorry. Apologize. But yes.
Okay. Any further questions? Is there any direct way to see Snebit's descent? Do you are Motivic Cohomology?
I don't know. Actually.
Yeah.
Probably. Oh no. Sorry. No. Once you establish Gersten resolutions, you can establish Nisnevic descent.
How it works?
Right. Once you have Gersten injectivity, you can establish Nisnevic descent.
Okay, I'll think about it.
You should ask Arnab knows this.
Okay. Yeah.
Gersten XR gives you Nisnevic. Gersten XR is the thing that bridges Zariski and Nisnevic. It's like kind of the same.
Okay.
Yeah. Okay. Yeah.
Thank you.
Okay, so then let's thank Elden again.